Hello. Today our topic of discussion is nuclear fission. You had already studied this nuclear fission in your plus 2 classes. Today in this class we are going to recollect or remember all those things. What is nuclear fission? It is a process in which the nucleus of an atom splits into two or more smaller nuclei along with some byproduct particles. You can simply say nuclear fission as a splitting of a heavier nuclei into lighter nuclei. So heavier nucleus is splitted into lighter nuclei. In the last class we had seen binding energy curve, isn't it? In the case of elements or nuclear with heavy mass number or high mass number, those nuclei will undergo nuclear fission so that their mass number gets decreased and they can come towards the region of greatest stability. So nuclear fission is the process which helps the nuclei to attain stability, and it was found out by O. Hahn and F. Strassman in 1938, in which they found out that when uranium was bombarded with neutrons, lighter nuclei are formed along with the emission of neutrons. So this is a picture showing a nuclear fission. Here we are having a uranium-235 nucleus, which is a heavy nucleus, and this heavy nucleus gets bombarded with a neutron. So what happens? The neutron imparts its energy to the uranium-235 nucleus and it will become an excited nucleus. Now the excited nucleus undergo splitting and forms lighter elements along with the emission of neutron. So this is a process of nuclear fission, and in this process large amount of energy is also released. So a heavy nucleus, when splitted up into two lighter nuclei, the total mass of the lighter nuclei will be less than the mass of the heavier nucleus. This concept was also studied in the last class regarding the difference in mass, isn't it? That difference in mass is called mass defect, and the energy equivalent to the mass defect is known as binding energy, and when the nucleus gets splitted, the binding energy is released as energy. So here you can see the equation of nuclear fission, that is a uranium nucleus with 92-235 bombarded with a neutron forming uranium-92-236, which is in an excited state, undergo nuclear fission forming barium and krypton along with the emission of 3 neutrons and energy. The energy released in a process is known as Q value. So here the energy released or the Q value in this reaction is about 200 MeV. So in a single fission reaction, about 200 MeV energy is released. And we know that there are some byproducts also. Fission fragments are there, and there is also byproducts are there, and here the byproducts are neutrons. So the neutrons emitted in the fission process can cause further emission, and that process is known as chain reaction, nuclear chain reaction, in which a continuous nuclear fission take place, and that process is known as nuclear chain reaction. We had already said that we are bombarding the uranium nucleus with a neutron, isn't it? So the uranium nucleus will undergo an excited state. See the above equation. Here you can see a uranium 92-235 is bombarded with a neutron, resulting in uranium 92-236. Now uranium 92-236 is in an excited state, and it will try to attain stability by releasing energy, isn't it? And one of that method to release that energy is nuclear fission. So the uranium 92-236 can undergo nuclear fission with an release of 200 MeV energy. But the probability of fission is 85%. This uranium nucleus can undergo de-excitation by the emission of gamma rays also. So the excited uranium nucleus can either undergo nuclear fission or can undergo emission of gamma rays. And the probability of emission of gamma ray is of 15%. Now the fission process, we know we are having a heavier nucleus, and this fission process of a heavier nucleus is similar to the oscillations of a liquid drop. See, we know that the liquid drop is spherical in shape, isn't it? And you know how a liquid drop splits into two. There are oscillations. Oscillations takes place inside the liquid drop and it gets splitted into two. Here you can compare the nuclear fission as that of a liquid drop. See, in the left hand side you can see a liquid drop. And in order to attain stability, this liquid drop is separated into two. Here also in nuclear fission, when a neutron is hit on a nucleus which is spherical in shape, it is having extra energy. So this more energy make oscillations inside a nucleus like that of an liquid drop. So the spherical nucleus will transform into a spheroidal nucleus. Then again the nucleus gets splitted into two by attaining a dumbbell shape, and after that it gets splitted into two. So the nuclear fission, we can compare the process of nuclear fission to the oscillations of a liquid drop. If the oscillations are violent enough, the drop splits into two. Once again, the fission process is similar to the oscillations of a liquid drop. So the sphere shape becomes spheroidal, then it becomes a dumbbell shape, and at last it splitted into two like that of a water drop or a liquid drop. Now, what is the energy required by the uranium nucleus to undergo fission? That energy is known as critical energy. So critical energy is defined as the energy needed by the uranium nucleus to undergo fission. And from where this uranium is getting energy? By the bombardment with the neutron, so that the neutron exchanges its energy to the uranium nucleus on colliding with it. So for uranium 92 235, on capturing a neutron, it gets an excitation energy of 6.5 MeV from a neutron. But it needs only a critical energy of 6.2 MeV. So what happens? Uranium 92 235 undergo fission, because the critical energy needed for the uranium 92 235 nucleus to undergo fission is 6.2 MeV, but it is gaining an energy of 6.5 MeV, which is known as excitation energy, by bombarding with a neutron. But this is not the case when we consider a uranium 92 238 nucleus. So a uranium 92 238 nucleus, on capturing a neutron, gets an energy of 5.2 MeV. But it needs a critical energy of 5.9 MeV to undergo fission. So is there any chance for uranium 92 238 to undergo fission? No. So the uranium 92 238 will de-excite either by alpha emission or gamma emission. This uranium can undergo fission if it gets bombarded with a fast neutron. Fast neutron means its energy will be more. So on colliding with the uranium 92 238 nucleus, this fast neutrons will transfer its energy to the uranium 92 238 nucleus, so that it will have an excitation energy more than the critical energy, and it will undergo fission. In short, we can say that the excitation energy must be greater than the critical energy, so that the nucleus can undergo fission reaction. We had already said that there is byproduct in the nuclear fission, isn't it? Smaller nuclei which are known as fission fragments or fission products, along with byproducts. So we are having in each nuclear fission reaction, we are having neutrons as byproducts, and the average number of neutrons emitted in a thermal neutron induced fission of uranium 92 235 is about 2.5. So the average number of neutrons released in a nuclear fission process is 2.5. Now what happens to the fission fragments or the lighter nuclei? Due to the Coulomb force of repulsion, the fission fragments fly off with a very large kinetic energy. And when these fission fragments collide with the atoms, this energy is transferred to the nearby atoms. So the Coulombic repulsive force between the nuclei, fission fragments, helps the nuclear fission fragments to fly off or to move with a very high kinetic energy. Now what is nuclear chain reaction? We know that in each nuclear fission, uranium 92 235 produces three secondary neutrons. Now the three secondary neutrons produced in the reaction can bring or can induce the fission of three uranium nuclei, so that 9 neutrons are produced, and again these 9 neutrons can induce another 9 fission reactions, and this process continues. So a continuous nuclear reaction, fission reaction, is known as nuclear chain reaction. And you know that in each reaction 200 MeV is released. So a continuous fission reaction produces a huge amount of energy in a very short time. And we can control this energy or control this reaction. If this nuclear chain reaction is controlled, the energy released can be utilized or can be used for good purposes, like that of a nuclear reactor or nuclear pile. So controlled nuclear chain reaction is the basic principle of nuclear reactor. And if the reaction cannot be controlled, what happens? The energy released will bring out very bad effects, which led to the discovery of atom bomb. High explosion will occur, and that is the principle underlying atom bomb. So this is a picture showing the nuclear chain reaction. Here you can see a neutron hitting an uranium nucleus, splitted into barium and krypton along with the 3 neutrons and a large amount of energy. Here the energy released is shown in the red color. Now these 3 neutrons again undergo fission by hitting with 3 other uranium nuclei and produces again 9 neutrons, and this process continues. And this continuous reaction is called a nuclear chain reaction. Again another picture showing the nuclear chain reaction, where the purple color shows the neutron and the green color shows the uranium. See, in the leftmost side there is only 1 neutron. Moving on to the right side, 3 neutrons, then again 9 neutrons, and so on. Now, what are thermal neutrons? We had already said the word thermal fission, isn't it? So the low energy neutrons are known as thermal neutrons, or we can also say it as slow moving neutrons. It's having low energy, isn't it? So it will be slow moving. So low energy neutrons or slow moving neutrons are called thermal neutrons. And these neutrons are required for sustainable chain reaction. For the chain reaction to occur in an ordinary way, we need thermal neutrons. See, initially we are having a neutron, isn't it? Now as the fission process continues, more and more neutrons are produced. That neutrons are known as secondary neutrons, but that neutrons will be very fast. That's why we are saying energy is released in a very short time. So the secondary fast neutrons has to be slowed down by passing through several substances which are known as moderators. So the secondary fast neutrons produced in a nuclear fission must be passed through substances like paraffin, deuterium or heavy water, which are rich in hydrogen. So what happens? On colliding against hydrogen nuclei or protons, this fast moving neutrons velocities gets interchanged with the protons, and thus the neutrons are slowed down. And these substances are known as moderators. So moderators are the devices or substances which are used for slowing down fast neutrons. We are only interested in sustainable chain reaction, isn't it? Or we can say it is a controlled chain reaction. So for a sustained chain reaction, we need neutrons. And we know that some of the neutrons are lost due to the leakage and absorptions, and we also know that more neutrons are produced in as the fission process continues. So to have a sustained chain reaction, the number of neutrons lost must be smaller than the number of neutrons produced, because the chain reaction must continue. So the size of the uranium block must be greater than a certain critical value in order to attain a sustained chain reaction, and that size is known as critical size. The chain reaction once started will remain steady or increase or decrease depending upon the number of neutrons. So we define a new factor called neutron production factor K, which is the ratio of rate of production of neutrons divided by rate of loss of neutrons. So on one side neutrons are produced, on the other side neutrons are lost by leakage or absorption. So a factor called neutron production factor will help you to determine whether the chain reaction will be steady or the chain reaction will continue or it will stop, and these are determined by the neutron production factor. K can be three values, either 1, less than 1 or greater than 1. If K is equal to 1, we can say that the steady chain reaction occurs. Then the size of the nucleus, the size of the fissionable material is called its critical size, and its mass is called critical mass. So if the chain reaction is steady, the size of the uranium nucleus used is known as critical size and its mass is known as critical mass. If a K is greater than 1, K greater than 1 means, see, we know that K is the rate of production of neutrons by rate of loss of neutrons. So production of neutrons is increasing, so that K is greater than 1. So K is greater than 1 means neutrons are producing more and more. So what happens? More fission reaction will take place and more energy is released. So the chain reaction will occur at a fast rate, which results in explosion, and this case is known as supercritical case, and this is how an atom bomb works. Now what happens if K is less than 1? K is less than 1 means rate of loss of neutrons is more. That means the neutrons produced in the fission reactions are absorbed more. So what will happen? After some time there will no more neutrons. So what happens to the chain reaction? The chain reaction comes to a stop or comes to a halt, and such size of the material used is said to be subcritical. So depending upon the value of K, that is neutron production reproduction factor, we can say whether the chain reaction is a steady or it will take place at a faster rate or it will come to a halt. So in this class we had discussed what is a nuclear fission reaction followed by nuclear chain reaction, thermal neutrons and critical size. Thank you.